We've been talking about equilibrium constants in terms of concentration, but we've been looking at a lot of reactions that occur in the gas phase. And we remember from our first semester of chemistry that for a gas reaction, the partial pressure of a gas is proportional to its concentration. The amount of gas that's present is proportional to the partial pressure it exerts. So we can use that to our advantage. So here's an example of a reaction where all of the reactants and products are in the gas state. Now what we're going to do is we're going to introduce a subscript on this equilibrium constant. Kc means that we're calculating that with respect to concentration. And so we would calculate the equilibrium constant with respect to concentration by taking the concentration of the products, SO2 squared, because it has a 2, times O2, and divided by the concentration of SO3 squared. That's what we've been doing. But now we can also say, well, we could express the equilibrium constant in terms of pressure. So we'll call that Kp. And here the pressure is going to be in atmospheres. What did we measure these concentrations in? Moles per liter, right? It was always in moles per liter. And so over here, we're always going to measure these in atmospheres. So the equilibrium constant with respect to pressure is the partial pressure of the reactant raised to the power of the coefficient times the partial pressure of the other product, and it's divided by the partial pressure of the reactants raised to the power of the coefficient. Exact same pattern. The difference is, instead of looking at the concentration, we're looking at the partial pressure. Okay? Now, if you go to look up equilibrium constants in a book or on the internet, you're most likely going to find Kc in terms of concentration. And Kc is not necessarily going to be equal to Kp. But there is a relationship, and so we're going to derive that relationship. So what we need to know is that the partial pressure of a gas in atmospheres is not the same as its concentration in molarity, right? It's not the same, but there is a relationship. So let's relate molarity of a gas to gas pressure. Well, what equation do we like to use for gases? The gas law, Pivner, right? PV equals nRT. So molarity is units of moles per liter, right? And in this equation, what represents moles? N. So N and volume in liters is V, right? So the number of moles of gas divided by the volume is the molarity of that gas. So let's try to rearrange Pivner so that we can get N over V equals something. And I should have written that somewhere else. I'll just move over here. So I'm going to divide by V on both sides, because this is the part I want that all together. These V's are going to cancel out. And then I want to get rid of R and T on this side. So I'm going to divide by R. So then I have to divide by R over there. Divide by T here. Divide by T over there. So now we get N over V is equal to P over RT. The molarity of a gas is equal to its partial pressure divided by the gas constant times the temperature in Kelvin. Everybody okay with that? Now what we're going to do is we're going to use that relationship we just figured out, where the molarity of A is equal to the partial pressure of A divided by RT, and we're going to look at our generic equation, and we're going to try to find the relationship between Kp and Kc. So the equilibrium constant in terms of concentration is equal to what? Close. CD over AB. So it's the last ones over the first ones. So C, the concentration of C raised to the power C times D to the D over A to the A times B to the B. And yes, somebody's going to make a song out of that sometime. Now what we're going to do is we're going to plug this in for A. And it's going to be big and messy. So down here for A, I'm going to write PA over RT. And that is raised to the power of that lowercase a. For B, all we have to do is change the subscript on the pressure, right? The concentration of gas B in moles per liter is equal to the partial pressure of B divided by RT. We've got PB over RT. And then we'll do the same thing for the guys upstairs. PC over RT to the C and PD over RT to the D. Okay? That's a big mess, isn't it? We need to factor some things out. So there's RTs all over the place. Let's factor those RTs out and see what we end up with. So we still have Kc being equal to, now I've got 1 over RT to the C and 1 over RT to the D. I'm doing this the long, hard way. I'll probably regret that when I run out of space. And that is times, the stuff that's left is PC to the C, PD to the D, over PA to the A, and PB to the B. What does this equal right here? Kp. The equilibrium constant with relationship to, or in terms of pressure. So that is Kp right there. Now we just have to figure out what to do with this big, hello pointer, there we are, no? With this big mess. I don't know what happened. So here we go with those stupid exponents again, right? So what can we do with these exponents? Okay, technology glitch, but it got me more room on my slide. So we need to simplify this business over here. So that means we need to remember how exponents work. If you multiply two things raised to an exponent, what do you do with the exponents? You add them. And if you divide, you subtract. So we have 1 over RT here, and we've got C plus D minus A minus B. How's that for an exponent?
B minus A plus B. No.
Well, it could be minus the quantity A plus B.
Oh, yeah, I've heard C too.
But I prefer to think of it this way. And then this guy over here is Kp. So we've got Kc equals this business. So this gets a little bit awkward, and so we're going to say delta N is going to be equal to C plus D minus A minus B. So delta N is the difference between the number of moles of product and the number of moles of reactant. So you take the number of moles of gases that you end up with and subtract the number of moles of gases that you started with. Again, we have that pattern of delta being final minus initial. It's the reactants minus the products. So did we gain moles of gases? Did we lose moles of gases? Sometimes delta N is 0. There's no net gain or loss in the number of moles. And then this is 1 over RT, and so what I'm going to do is I'm going to multiply both sides, and so what we're going to come up with is that Kp equals RT to the delta N times Kc. And there we have a nice little package. Oh, I should put parentheses in here. Those are important because it's R also raised to that power. This relationship allows us, if we know what the equilibrium constant is in terms of C, we can calculate it in terms of pressure, if that's what we want to be able to use. Any questions? Stunned silence. So there it is, all pretty. So delta N represents the difference between the number of moles of products and reactants that are in the gas state. And when the total number of moles of gas, so you like details, you got to put up with this. When the total number of moles of gas is the same before and after the reaction, then Kp is equal to Kc. Because in that instance, Kp equals Kc times RT raised to the 0 power. Anything raised to the 0 power is 1. That's equal to Kc. So sometimes, for some reactions, they are the same. But you can't assume that the numbers are the same. So let's do a practice problem. Consider the following reaction and corresponding value of Kc. What is the value of Kp at this temperature? Well, let's write down that equation we just learned. Kp equals Kc times RT raised to the power delta N. We need to figure out what delta N is. How many moles of gaseous products do we have? 2. And how many moles of gaseous reactants do we have? 2. 2 minus 2 is 0. So Kp equals 6.2 times 10 to the second. Is that kind of a letdown for anybody? It happens. It happens. Now, units on K. We've kind of glossed over this because the concentrations have units of moles per liter, and sometimes if you were to put the units in there, they're not going to cancel out, and yet we've been using K as if it were unitless. Well, formally, what we're putting in there for concentration or pressure are actually ratios of the concentration relative to 1 molar or the partial pressure in atmospheres relative to 1 atmosphere. So if you have a concentration of 3.7 moles per liter, what we're actually putting into the equilibrium constant expression is 3.7 molar to 1 molar. And so each of the concentrations are actually a unitless quantity. And that's why K ends up being unitless. So I tell you that for those of you who care about things like that. Bottom line, as long as we express concentration in molarity and partial pressure in atmospheres, you can simply drop the units and you'll be fine. This is one of the very, very few times where I can say with a clear conscience, forget about the units. Almost everywhere else, you need to write down the units. But here we can just kind of skip them. So that's how K is unitless, even though it doesn't look like it should.